Have you ever wondered how a small hydraulic jack can lift something as heavy as a car? To lift a car using the hydraulic jack, all we need to do is push the handle down repeatedly, which requires very little force. The hydraulic jack amplifies this small force, making it powerful enough to lift a 2-ton car off the ground, something we could never do by just using our strength. So how does the hydraulic jack generate such a significant amount of force? Where does this extra power come from? Let's take a look inside the hydraulic jack to understand the science behind it. A hydraulic jack is made up of many different parts. At the top of the hydraulic jack is the saddle. This is the part that touches the undercarriage of a car or some heavy machinery. The saddle can be adjusted to different heights. It's connected to the ram piston with a threaded screw. The ram piston is like the heart of the hydraulic jack. It's located inside the working cylinder and is responsible for applying the force needed to lift an object. The oil, which is used as the hydraulic fluid, is stored in the oil tank. The reason for using oil as a hydraulic fluid is that it doesn't change volume under pressure. The hydraulic jack is operated using the handle, which is like a long lever that is pumped up and down to create pressure on the hydraulic fluid. The pump piston resides inside the pump cylinder and is controlled by the handle. The pump piston is what applies pressure to the oil. There are 2 check valves to make sure that the fluid only moves in one direction. The release valve facilitates lowering the ram piston by releasing the pressure in the system. Now let's take a look at how these components work together to lift a car. The process starts when the handle is lifted, which causes the pump piston to move up. This upward motion decreases the pressure in the pump cylinder. As the fluids move from high to low pressure, the drop in pressure allows the oil to flow from the tank into the pump cylinder. The moving oil pushes the pump check valve up, opening the path for the oil to flow freely into the pump cylinder. When the handle is pushed down, the pump piston moves down too. This increases the pressure inside the pump cylinder, which makes the oil starts to flow into the connected tubes. The high pressure pushes the pump check valve down, stopping the oil from going back to the tank. At the same time, the pressure from the oil pushes the ram check valve up, allowing hydraulic fluid to enter the working cylinder. Oil entering the working cylinder pushes the ram piston up. As the ram piston moves up, it lifts the car off the ground. When the handle is lifted again, the pressure in the pump cylinder goes down. This lets oil flow from both the oil tank and the working cylinder back into the pump cylinder. The oil flow from the working cylinder pushes the ram check valve back in place, stopping oil from going back into the pump cylinder. At the same time, the oil from the oil tank pushes the pump check valve up, allowing oil to flow freely into the pump cylinder. When the handle is pushed down again, the whole cycle repeats. To return the hydraulic jack to its resting position, a passage is opened that connects the working cylinder directly to the oil tank. This passage is typically sealed by a release valve, which is held in place by a screw. When the release valve is unscrewed, it opens the passage, allowing hydraulic oil to flow back into the reservoir due to the gravity acting on the ram piston. This is how a hydraulic jack lifts an object. However, the question that from where a hydraulic jack gets extra strength to lift a heavy object still remains unanswered. Let's find the answer to this question. Hydraulic jack works on the principle of Pascal's law and the law of the lever. Pascal's law states that when the pressure is applied to a fluid in a closed system, that pressure is transmitted equally in all directions throughout the fluid. Let's say when the pump piston is pushed down, it applies pressure Pp to the oil in the pump cylinder. According to Pascal's principle, this pressure Pp is not confined to the area where the force was applied. It is transmitted equally through the oil to all surrounding areas. That means the pressure Pp generated by the pump piston will also be transmitted undiminished through the oil to the ram piston. Let's say the pressure transmitted to the ram piston is PR. Then according to Pascal's law, PR is equal to PP. As we know that the pressure is force per unit of surface area, the equation can be rewritten as Fr divided by AR is equal to Fp divided by AP, where Fr and Fp are the forces applied to the ram and pump pistons, and AR and AP are the surface areas of the ram and pump pistons, respectively. The equation can be rewritten as Fr is equal to Fp multiplied by AR divided with AP. This equation shows that force applied to the ram piston is directly proportional to the ratio between the area of the ram piston and the area of the pump piston. If the ratio between the area of the ram piston and the area of the pump piston is 4:1, or in other words, if the ram piston is 4 times bigger than the pump piston, then the output force will be quadrupled, provided that the pressure remains constant. Pascal's law explains how a hydraulic jack amplifies the input force. Apparently, it looks like hydraulic jack is creating energy out of thin air, which is against the law of conservation of energy, which states that energy can neither be created nor destroyed. However, this is not the case. While the force is amplified, the increase in force comes at the cost of distance. When the pump piston is pushed downward, it displaces a certain amount of oil. As the oil is an incompressible liquid, it moves the ram piston up by the same volume. As the area of the ram piston is larger than the pump piston, it only moves up by a small amount to achieve the same volume. The increased force comes by trading off distance, ensuring that the total energy input equals the total energy output, thus complying with the law of conservation of energy. The hydraulic amplification of force is just one of 2 principles used in a jack. The more significant force amplification comes from the jack's handle, which acts like a lever. According to the law of the lever, mechanical amplification results from the ratio of the lever's active arm and passive arm. The active arm, denoted as A, is the distance from the pivot point to the handle, while the passive lever arm, denoted as B, is the distance from the pivot point to the pump piston. For example, if the lever arm A from the pivot point to the handle is 10 times larger than the distance B from the pivot point to the pump piston, then according to the law of the lever, the force will be amplified by a factor of 10. The total force amplification in a hydraulic jack is the combined result of hydraulic and mechanical amplification of forces. From the powerful piston to the precise control of the release valve, the hydraulic bottle jack is a great example of how science and engineering can work together to solve practical problems. By leveraging the principle of hydraulics and mechanical advantage, this tool can lift enormous loads with ease and precision. Next time you use one, you will have a deeper understanding of the technology behind it. And we hope this animation helped clarify how this incredible tool works.